Welcome back to an introduction to the Discrete Fourier Transform. This is lecture 3, where we'll talk about aliasing and the Nyquist frequency. We'll talk about sampling first. So given a signal y of t, a continuous function, and L is the length of the signal, we want to sample from this continuous function. And for us, we're going to sample at the rate of 44,100 times a second. This is a standard CD quality sampling rate. And so we want to figure out the number of samples that we get from this sampling rate. So we multiply the length of the signal by how fast we're sampling. So L times Fs. And then we might have to round it down, use the floor function to round it down if this is not an integer. And that will give us the number of samples from our sampling. So in Python, we just simply multiply L times Fs, and then we just cast it into an integer. That will give us the total number of sample. And so the time sample is all the time that we pick these samples, so t0 to t of n minus 1, because they had n samples. And the distance between each of these sample time is delta t, and that's simply the difference between the two consecutive sampling time. And this sampling interval is actually 1 over the sampling rate. We'll do an example in a second to describe that. And then in Python, the way we do that, we've done this in the previous video already, but we use NP linspace to take out n samples from the interval from 0 to L. And now, previously, we didn't really do this, but from now on, we have to be careful. We have to say that the endpoint, we have to say that we don't want to pick the endpoint. So we don't want this L. And I'll explain that in a second. So we say endpoint is equal to false. So this is so that this spacing is consistent with this delta t, which is the 1 over the reciprocal of the sampling rate. So we want everything to be matched up exactly. And then from the sample, the time sample, we can plug in the function into those time value, and that's how we get the sample value from the continuous function. And so previously we said that we just abbreviate this with using indices rather than time. So again, we have n sample. The first sample is y0. The last sample is y of n minus 1. Okay, let's do an example in Python. Okay, so suppose I want to sample a function from the 0 to 1. So this is 1 second interval. And we want to sample at the rate of 5 hertz. The question here is, what is the sampling interval? In other words, how far apart each of those time sample? Well, if we sample at a rate of 5 hertz, that means that we sample the delta t should be 1 over 5, which is 0.2 second. So again, if we sample 5 times a second, then that means that we're sampling every 1/5 of a second. Every 0.5 second will give us 5 times a second. So this should be our interval between the sampling times. Now, so the problem is that if I were to try to do this in Python, well, previously we were kind of sloppy and we did something like this. I want to go from 0 to 1, that's the time, and I want to do, I want to sampling at 5 hertz, and so, actually let's do this. So I want Fs to be 5 hertz, and I want n to be, again, this is I also want L to be 1 second. So from the formula we saw earlier is L times Fs, and I cast it down to an integer. This gives us the total number of samples. So I want to take n sample. Now if I do this, notice that this is actually not consistent. Notice that when I do this, I do have 5 sample. That's what I want. But the interval, the sampling interval is actually 0.25, which is actually bigger than 0.2. So this is actually not correct. So for this to be consistent, again, if I'm sampling at this rate, my sampling interval should be the reciprocal, which is 1 over 5. So the way I do this, I say endpoint is false. This will not pick the number 1 as the endpoint. So 1 is no longer part of the endpoint. And if I do this, notice I get now this interval is consistent with the sampling rate, which is 0.2 second between consecutive time sample. It's a small minor point, but in the homework for this lecture, there's some question about aliasing that you have to be really precise about, and so that allows us to be consistent with the sampling rate. Okay. And so here's aliasing. This is a very important idea in signal processing. If I have a continuous sample, our sample is discrete data, and so this is only approximating the actual continuous signal. And so when we sample at discrete times, we lose information about what happened between the samples. So this is an approximation. We have to be careful that our approximation is valid. And so this leads to a problem known as aliasing. The idea is that we're not really sure if our sample really matched up with the actual original data. So a good example of this is, suppose I have some signal. I don't know what the signal is, and I'm going to take 6 samples from this signal. And so here's the 6 samples. Of course, these samples could come from this signal, which is good, because then that means our sample match up exactly to the original continuous function. But our sample could also be from this signal. The problem is that when we sample, our data is approximate, and it might come from many functions. In fact, there's an infinite amount of function from which our sample can come from. And so this is aliasing. Okay, let's see this in Python. Okay, I'm going to create, so my sampling rate is 5 Hertz. I'm going to do it for 1 second, just like before. And so let me give you the data point for this. So TS is NP length space, just like before. I'm going to go from 0 to 1, N, and again I want endpoint to be false. Then my Y sample is NP.sign. Let's just do a sign function. 2 times NP.pi times TS. So this is a frequency. Let's put in this number 1 here. So this is a 1 Hertz frequency. And so let's plot this figure. So again, plt.subplots. I'm going to do a scatter plot of this. TS versus YS. So notice this is we're sampling from the sine function, and we're sampling it this 5 sample here. Okay, so here it is. So again, we don't know the original function. So but the problem is that there's many functions from which this can come from. And so let's see one example of this. Let's do a continuous original function that has 1 Hertz. So this is the one that actually match up with what we want. So I'm going to copy this. And I'm gonna to make it continuous, we simply do like 100 points. Just do a lot of points. That way, it looks continuous. So let's call this T1, and let's call this Y1, and I'm gonna plot it again, but this time also on the same axis. So TS1 versus YS1. Let's see. Okay, let's see why this doesn't work. 0, 1, 100 endpoint is false. Oh, I want this to be TS1. There we go. Okay, so our sample match up exactly to our 1 Hertz wave. But the problem is that we might also have another wave. So let's do this again. So now I don't need this one. I'll use the same one. So now let's call this YS2, and now I want to sample from. Let's try this one. Let's try 6, and I'm going to plot this one. Notice our sample data could have come from either of these functions. So that means that our data is not accurate in this, some ambiguity, and so this is aliasing. And of course, actually, it turns out you can actually do this for example, -4. We'll talk about where these numbers are coming from later. This is another example. So there's a lot of examples. Let's actually do another one here. So let's call this Y3. So let's put all of them together. So this is Y3. So notice I just generated 3 functions, and our sample data could have come from any 3 of them. So that's aliasing. It's not clear which one it comes from. Okay, so let's kind of see another animation that illustrates aliasing. So here I have a Java program used in processing. Okay, so this is a great analogy that helps you understand aliasing. So here, suppose I have a wheel. It's going to spin. So sampling right now is off, so I'm going to increase the frequency. So if I increase it, so this is going at a rate of 0.5 hertz. If I increase it again, it's going to go faster. This is frequency here is 1 hertz. That means that it's one time per second. I can go up. So this is now 2 times a second. I can keep going up, and this is going to spin faster and faster. So this is the wheel's frequency. Now sampling is basically like turning. Imagine that this is the wheel spinning, and I want to turn off the light. So I don't see the wheel, and sampling is basically turn on the light every so often, every equal spacing, and when we turn on the light, we see it just for a second, and then we turn it off again. And so again, if the light is on, then this is continuous. We see everything. But let's turn sampling on. So let's say, let me turn it on now. So now sampling is on. Notice that our wheel frequency is still 1 hertz, and even with the light flickering or with sampling on, what we observe is still 1 hertz. So what we observe match up with what is actually the frequency. Now if I increase it, same thing. Again, if I turn it off sampling, this is the wheel spinning. If I turn it on, then again sampling is still accurate. Our observed frequency, this looks like it's 1.5 hertz, and that matches up with what the actual frequency is. Now, as we get higher up though, again, we're sampling here at 4 hertz. I forgot to mention that. So we're sampling 4 times a second. So again, if I sample 4 times a second, right, consistently the wheel frequency and our observation is the same. The problem is that as I get bigger, as my frequency gets faster, this sampling rate will not be able to adequately spot some of the high frequency components. So for example, if I go up to say 2.5, notice the actual frequency, if I turn it off, is 2.5, which is very fast. But if I turn on sampling, it actually looks like it's negative 1.5. It looks like it's going the opposite direction. If I keep increasing it, so again, the actual frequency again is 3 hertz, but with sampling, I'm only sampling at 4 hertz. So this frequency failed to catch this frequency, so that our observation looks like it's negative 1 hertz. So the actual frequency is 3, but our observation is negative 1. It looks like it's going the wrong direction. In fact, if you've ever seen those Western movies, the wheel is spinning, and as it's spinning, you sometimes see the wheel spinning backwards. Right? This is actually aliasing in videos, in movies. So if I keep going up, notice now the frequency is very high. So let me turn off sampling. So this is very fast, but if I turn on sampling, because I'm only sampling at 4 hertz, my observation looks like it's only 1 hertz. So even though it's spinning very fast, I'm only seeing a 1 hertz frequency. So what we say is that this 5 hertz alias into a 1 hertz observation frequency. Again, if I keep going up, same thing. So this is spinning very fast, but my observation is only negative 1 hertz. So we say that this 7 hertz is alias into a negative 1 hertz. So this is the limitation of sampling. And so a couple observations. One observation is that if my frequency is between negative, if I take the sampling frequency divided by 2, if my frequency is between negative fs over 2 and positive fs over 2, then there's no aliasing. So let's go back down. So again, if I'm between 2 and minus 2, right, the frequency sampling is 4, so it's if I'm between negative 2 and positive 2, the observation and the frequency match up. Right? Everything match up, so that there's no aliasing. But if I'm outside of this interval, then there's aliasing. If I'm outside of the negative 2 to 2, right, then I have aliasing. So if I'm outside of this frequency, then f is alias back into it. So in this case, for example, 3 is alias into a negative 1. So the idea is that we have to be inside of this frequency for our sampling to be accurate. So whatever the sampling rate is, it needs to be divided by 2, and you can look from negative to positive, but outside of this, we have aliasing. And another thing I want to point out is that to get from the actual frequency to the alias frequency, we simply take the actual frequency and subtract a multiple of, subtract or add a multiple of the sampling frequency until we get something that is inside of this range. So for example, let's do an example. Let's go up to say 7, right? 7 is outside the range. If I subtract 4, I get 3, but 3 is still not inside this range. So I subtract 4 again. 3 minus 4 is negative 1. So once I'm inside the range, then that's my observation frequency. So this is the formula that convert actual frequency to observed frequency. So you basically subtract or add some multiple of the sampling rate. So there it is. There's aliasing. Let's go back. So what this says is that if I have a function that is if I'm sampling at this frequency, the sampling rate, we cannot distinguish between the function of f0 hertz or a function of f0 plus a multiple of the frequency sample. That's what we saw earlier, that high frequency will alias back into the low frequency, so that we can distinguish between those functions. And so, for example, if I'm sampling at a rate of 6 hertz and my original wave is 1 hertz, well, my sample data could also have come from 7 hertz, right? Adding 6 again to give you 13, adding 6 again, this should be 19. So that's a mistake. But the point is that if we keep adding 6 hertz, then any of these functions could have been our sample data. In the same way, I can subtract 6. 1 minus 6 is negative 5. Minus 6 is negative 1, 11. So a function could have been any of these functions, and the sample data would have been the same. So this is again the problem with the aliasing. So here's the sampling theorem. So how do I solve this problem? Turns out that, again, in the animation we kind of saw this, is that if our signal, the point here is that if I'm sampling at a rate of fs, then I need all my frequencies in my signal to be less than half of the sampling rate. So provided that my original function have only frequencies that are less than half of the sampling rate, then my sample is accurate. But if my function has frequencies that are higher than this, then that means we have distortion. We have those higher frequencies will alias back into the range, and then we introduce frequencies that are not actually there. And so this is sampling theorem. And so this frequency, the sampling divided by 2, is called the Nyquist frequency. So again, I need all my frequency to be less than the Nyquist frequency for my sampler data to be accurate. So here's an example. This function has some 3 frequency, 1 hertz, 3 hertz, and 4 hertz. And so that says that so that the higher frequency is 4. So that means if I sample, say for example at 10 hertz, 10 divided by 2 is 5, so Nyquist would be 5. Notice that all my frequency here is less than 5, so that means that if I sample at least 10 hertz, at a rate of 10 hertz, then my data would be accurate in reflecting all of these frequencies. So here's a picture of that. So this is the original function, the continuous curve. Notice this function has 3 frequencies. And again, because the highest frequency is 4, if I sample 10 times a second, 10 hertz, then here's my data from sampling 10 times a second. The sampling theorem says that this data is enough to recover the original function. In other words, if I sample 10 times a second, then there's no aliasing, and this sample data, when I use the discrete Fourier transform, we were to be we can reconstruct the original signal, the original data, from this data. Okay, so something that will be useful later is that, and something that we'll prove in the next lecture in one of the homework assignments, is that when you have a spectrum of a real signal, in other words, if I look at the frequencies of any real signal, this spectrum is again, the frequency representation is symmetric around the 0 hertz. What that says is that if I have a frequency f in my signal, then there's also a negative f frequency also in my signal. So for example, here's the example we saw earlier. This has 1 hertz, 3 hertz, and 4 hertz. Well, this theorem says that this function also has a negative 1 hertz, negative 3 hertz, and negative 4 hertz. In other words, when I do the discrete Fourier transform that we saw from the first lecture, we'll see all the positive frequency, and we'll also see the symmetry where all this frequency, when I reflect it over the origin, all these negative frequencies also present in the same amount. And so this is just a characteristic of a real signal. And the reason why for this is because, as we see in the next lecture, we use a complex exponential to model our original function. And complex exponential, there's a complex equation that we'll talk about that kind of makes explains why this is the case. Okay, and so the recap here is that when we sample at this frequency of fs, the discrete Fourier transform can only detect frequencies between negative fs over 2 and fs over 2, between negative the Nyquist frequency and the positive Nyquist frequency. And because of every Fourier signal has a symmetric spectrum, everything from a positive frequency also occur in negative frequency in the same amount. So really, when we do discrete Fourier transform, we only look at from 0 to the Nyquist frequency. Those are the frequencies that we want to look at, because everything else is just symmetric. And everything outside of this is alias, so we want to make sure that we don't look at those. And so in fact, the Numpy library have, in FFT, the module FFT, it has all FFT, which will give you the real values, because when we have real signal, then and this function right here will actually give us only the spectrum from here to here, and it won't give us the spectrum outside of this. So we'll see this more when we do the homework assignment. Okay, so here's an example of distortion that is caused by aliasing. Suppose I have I play a violin and I play a frequency of 750 hertz, and I'm sampling at 10,000 hertz. So suppose that the violin has the following harmonics, and these are multiples of the fundamental frequencies. So say that when I play this note, it has all of these harmonics that gives it that sound. Now, because I'm sampling at 10,000 hertz, that means that my Nyquist frequency is 5,000 hertz, which is around right here, and that means that everything outside of that would now be aliased into it. And so let's kind of see this. So that means everything outside of 5,000 hertz is aliased. So for example, 5,250, we can't detect that frequency because we're not sampling fast enough. So how do I get the alias frequency? You subtract the frequency rate. So you subtract 10,000. This subtract 10,000 is negative 4750. 6,000 minus 10,000 is 4,000, negative 4,000. All these frequencies are now aliased into the negative range, and so that we can't detect these frequencies. And so this is not good, because now we suddenly have these alias frequencies that are not the actual original frequencies. They're now they distort the original signal. So it turns out that our ear cannot distinguish between negative and positive frequencies, and so we take those negative and we simply we take those negative frequency and we simply make it positive, because our ear can distinguish between the two. So now this is our new harmonics, and unfortunately, because of that of aliasing, now we have signal that is not in the original harmonics. So for example, all these some of these signals are not from the original harmonics, and so now we have a distortion of the original signal, because some of these are no longer integer multiples of the fundamental. So that's the problem with aliasing. If we're not careful, we might distort the signal. So let's talk more about harmonics. So again, harmonics, we mentioned this I think when we did in lecture 1, but if I have an audio from 0 to L, then the fundamental frequency is 1 over L. So if this is the period, the frequency is 1 over L, and this is the fundamental frequency. This is the frequency that basically complete one cycle in this interval. That's why it's called the fundamental frequency. It does one cycle in the interval. And so note that if you take, we saw earlier that Fs times L is the number of sample. So this, if I solve for, if I use that formula, I can actually do this another way. If I solve for L, or 1 over L, then I get that 1 over L is the same thing as Fs over N. So the fundamental frequency can be computed by 1 over L, or can be computed by taking the sampling rate and divided by N. So basically, here are the harmonics. 0 hertz. This is the fundamental frequency. This is 2 times the fundamental frequency, all the way to the Nyquist limit and beyond. And we saw earlier that this is the Nyquist limit. So everything after this is alias. So that means that we can throw those away. So these have now become negative frequencies. And so the discrete Fourier transform would try to detect the presence of these frequencies, the first half of this. The second half we saw is symmetric, so we don't have to worry about these. These are symmetric, so really we don't have to worry about the negative frequencies. We only look at the first half up to the Nyquist frequency. And so here's another example. If I have a function from 0 to 2, so 2 seconds, and I sample 4 hertz, then the fundamental fundamental frequency is 1 over L, which is 1/2 Hertz. I can also do it another way. I can also take the sampling frequency, 4, and divide it by 8. That's another way of doing that. So here are the 8 harmonics. 0, 1/2, 1. So these are multiple of the fundamental frequency. So here they are again as decimal. So again, because of aliasing, because we're sampling at 4 Hertz, the Nyquist frequency is 2 Hertz. That means everything above 2 is aliased back into the negative frequencies. So subtracting 4 from each of those give us the alias frequency. And we saw before that because there's some symmetry, in other words, we can detect the difference between this one and the one here, and the spectrum is the same for, so whatever amount I have for one frequency is the same amount for -1, so I can throw away those. And so the discrete Fourier transform, we're only going to look at these frequencies from 0 up to the Nyquist frequency. Okay, so why 44,100? Turns out that human hearing is between 20 to 20,000. So that means that to adequately sample all of those frequencies, we need to sample at least 40,000, right? 40,000 divided by 2 is 20,000. So that's why CD quality is around 40,000. Is exactly 44,100, because we need to make sure we have the ability to record all frequencies up to 20,000. So that's why we have that number. So typically before we sample anything, we do something called a low-pass filter. We remove everything above 20,000, make sure that, because if we don't remove those will alias and will distort our signal. So we need to filter out those things before we sample. Okay, so here's a summary of what we learned from this lecture. Aliasing happens when there are high frequency components, at least high frequency components in relation to the sampling rate. More precisely, we need to make sure that the highest frequency component is no more than half of the sampling rate, which is the Nyquist frequency. Any real signal has symmetric spectrum. If I have a frequency f in the signal, I must have a negative f also in the signal. The DFT detects integer multiples of the fundamental frequency. In other words, I detect all frequency from 0 to the Nyquist limit. And then, so you want to filter out these frequency first before we sample, so that we don't have this problem of aliasing and distorting the signal. Okay, thanks for watching.